I already did a video on relative acceleration, so this one's about proper acceleration. Okay, what is acceleration? Changing your velocity. And what is velocity? It's a vector with two things, speed and direction. Okay, so what is proper acceleration? Well, acceleration relative to space-time. Okay, that's what proper acceleration is. I want you to think, there's only two types of acceleration. There's proper acceleration and there's relative acceleration. Talk about relative acceleration and compare it to proper acceleration. Okay. Here's a ball, right? A spaceship with a red ball in it. It's going constant velocity right in the middle of nowhere. There's no planets or nothing. They're a million miles away. You got this blue ship with a blue ball in it, and it's going constant velocity, straight line. Everything's floating, so you know they're inertial. Okay, they're millions of miles away. Where they intersect is million miles away. They are both inertial frames. Okay, straight line path, constant velocity. Everything floats, no ground. But if I split this up into two equal angles and divide it up into 3 units of time, you can plainly see the paths are accelerating towards each other. Okay, that's a type of relative acceleration because there's no force onto the balls. Okay, see, that's the difference. See, relative acceleration, there's no force on the object. Proper acceleration, you have to have some force. Okay, so yes, their paths are accelerating towards each other. Technically, you can say they are accelerating towards each other, but the more technical way to say it is they are relative accelerating towards each other. You know what I mean? Because it's not because they're accelerating, it's just because their paths so happen to cross a million miles from now. Okay, but let's look at the second example. Okay, that has relative acceleration, and you see it's a falling ball. This is the Earth. Same thing. Cut it up into 3 units. You can see the acceleration. Now this red line, this is in curved space. So this is a straight line. Okay, that red line. All right, that's the inertial path. All right. So if the ball follows that inertial path, right, it isn't just like up here. It's just that the path is accelerating, not the ball. Okay, just like up here. And when that happens, the ball, in both the instances, stays inertial, but it is accelerating in some form. Its path is, it's not really accelerating, its path is accelerating, right? The path is accelerating, right? So the ball isn't accelerating at all, okay? So what is accelerating, okay? It's the space-time. Proper acceleration is happening on the space-time, right? That's why this is curved. Curved lines on a graph represent acceleration. But the ball isn't accelerating. If the ball had an accelerometer, it would say it was inertial. It's not accelerating, it's floating, just like in outer space. It's just in outer space, there's no gravity to, accelerate the space-time down and make the path look like it's curved. Right? So the ball falling, that's a relative acceleration of the falling ball, right? The space-time, now that's a proper acceleration. The space-time is being proper accelerated down to the Earth. Okay? So you got the floating ball test, you got the accelerometer test. You hold a ball out, if it floats, it's not accelerating. If it doesn't float and it goes to a ground, then it's accelerating. That's proper acceleration. Not the ball, the space-time if you're on Earth. But if you're on a spaceship or spinny thing, it isn't the space-time that's accelerating, it's the ground. This ground is spinning, this ground is accelerating up, right? All 3 instances, a falling ball is inertial. You feel it. When you have proper acceleration, you can feel it, okay? There's a force, right? And keep in mind, obviously, if you're going to be accelerated 1 millimeter per 10 years, you're not going to feel it. Don't be woke. Okay, use your common sense. You're still being accelerated even if you don't feel it. Okay, you know what I mean? If you're moving and you're changing your velocity, or you're changing you're changing your speed, or you're changing your direction, you're accelerating. Whether you feel it or not, it's proper acceleration. Right? You just have to ask: are you stuck somewhere? Stuck to the ground? Are you accelerating toward? Are you deviating from your straight line path? Your straight, and if you're in curved space, your straight line geodesic path. Are you doing that? Okay, like this ball right here, it's not deviating from its straight line path. This ball isn't deviating from its straight line path. It's inertial. They're inertial. They're not accelerating. The space-time is accelerating. Now, I want you to look at these 3 ways that you can accelerate something. I mean, other than throwing a ball. Obviously, with your hands, you can do it that way. But these are the 3 types of proper acceleration. You have a spaceship with a rocket, right? There's a ground, everyone's stuck to it. You can have a spinny thing. It spins, rotates, okay? There's a ground, everything's stuck to it. You can have Earth, right? There's a ground, everyone's stuck to it, right? Right? So, and you can feel it, you know what I mean? Earth is not following its inertial straight line geodesic path. See, this falling ball is following its inertial straight line geodesic path. The North and South Pole, they are not following their inertial straight line path. Okay? See, this geodesic, that whole time going through time, because this is going through time, not going through space. We're pretending the Earth is just standing there. This geodesic is the same spatial coordinates. Here, 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 here. Same here. Same spatial coordinates down here, 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 here. Okay? And these 2 spatial coordinates want to be right here in the future, right? But the North and South Pole, they are not following that inertial straight line path, are they? No, they're following the dotted line. I didn't do a dotted line here. So they are deviating, they're changing their direction. Okay? And so therefore, that's called proper acceleration. Because space-time is following this red line. It's accelerating down, but you are not. You are, see, gravity only affects space-time. It accelerates space-time down at 9.8 meters per second squared. If you are falling with space-time at 9.8 meters per second squared, then relative to space-time, you are not moving. So you are not accelerating, and you're not proper accelerated. You're just sitting there floating, okay? So you hit the ground. Then what happens when the ground happens? You're falling, you hit the ground. The space-time coordinates keep going down, but you're standing here. The ground is preventing you from following your inertial straight line geodesic path, see? Just like here. The ground prevents you from, because you want to go off on a tangent, right? But the ground prevents you from taking that inertial straight line path. Same here. You just want to float there and whatever. But the ground comes up and prevents you from, if you have a ground preventing you from taking your inertial straight line path, and you get off of that inertial straight line path, that is proper acceleration, right? You feel it. You have to do something. Here you're just floating. Here you're just floating. You're not doing anything. Now I'm going to give you an exact definition, right? First you need to understand time dilation, okay? Let's say this is a photon clock. Photon goes back and forth. Each time it hits one of the plates, it's a second. We all know that, right? You move. Now the photon comes down, but you move, so the top plate is over here, so it has to travel a lot longer, right? Well, this same concept happens with all physics, okay? Here's your synapses. See how synapses don't touch each other in the brain. They communicate by throwing photons at each other, right? So your line in between that is that small, but when you move, now you've elongated it. You made it longer. Same way with the hands of the clock. They don't just move when the hand is told to move. First atom throws a photon, moves, throws a photon. Then this atom moves and throws a photon, and so forth. And then when they all get the message, they all have moved. But what happens when you move through space? Now the photon comes down, but now you've moved, so it takes longer That's what time is, okay? Time is this line, right? And the longer this is, if you make it longer, then you dilate time, because you're not slowing down time, you're slowing down the flow of information, right? So you can't get the information from atom to atom, synapse to synapse, photon plate to photon plate. All physics, electronics, metabolic rates, whatever, they're all reliant on this. And if you make it longer, because the speed of light is constant, right? So if this is a second here, right, or a unit of time, now you're moving. Now you've stretched out. It takes longer to pass the information on. You can only, this is twice as long, right? Your gamma. You're only going to think half as fast. So you want to know the exact definition of proper acceleration. The exact definition is making this line bigger or smaller. That is it. Proper acceleration is making the line change length. Okay? If you change the length of this light has to travel, right, by moving, you are accelerating. That's a proper acceleration. Whether you're doing it because the planet won't let you follow the gravity, the space-time, whether it's the ground won't let you, whatever. Whether it's the ground here, the ground here, or the ground here, they're preventing you from going on your inertial straight line path, and the photon goes 186,000 miles per hour, right, or second, relative to space-time. Yeah. So if you move, it's going 186,000 miles per second here. Guess what? It's still going 186,000 miles per second. But all physics rely on atoms communicating, or synapses communicating with information carriers, and those are mostly photons, and all information carriers go at 186,000 miles per second. So you have slowed down physics itself when you accelerate, okay? So changing this line, boom, accelerating. Now, let's say you're going through space, right? And you start accelerating, right? So you're making this line get longer and longer. You're making the information slow down, the flow of information, because now when you stop, you start floating, you're inertial. This line isn't changing. It's stuck there, though. Now your information is stuck here. It looks like it's, what, 2-3 times longer to get your information from synapses to synapse, to atom to atom. Now you're stuck there, okay? Now if you slow down, or if you speed up, this line will get longer. If you slow down, it'll get slower and slow. And this is a form of acceleration, see? Because you're changing the length of this line down to this. If you change the length of this line, then you have accelerated. You have been properly accelerated. That's proper acceleration. See, over here, you're not changing your line. Whatever your line is, it's stuck there. You're just going, you're not proper acceleration. That's literally the definition of proper acceleration, okay? And how do you prove that something? Your accelerometer, okay? You can hold the accelerometer or put the accelerometer on whatever you're, like the planet or whatever, and see if it's accelerating. You know what I mean? It'll tell you. The floating ball test, you hold something out, let go of it. If it floats, you're inertial. If you're, if it's doesn't float there and it falls to a ground, then it's accelerating. Acceleration is relative to space-time. Okay, what's the exact definition? Changing this length, changing the what a second is. Because let's just say this is a second, or unit of time. Now this is a second. Now this is a second. Okay, so acceleration is the changing of the flow rate of time, or the flow rate of information to do all physics. Earth, right? You can have an infinitive number of ships, different sizes, different whatevers. The spinny thing. You can have an infinitive number of sizes, infinitive of whatever, as long as they have 9.8 meters per second squared. They will be time dilated and have gravity, and it'll be every physics law or experiment, you'd have the same results. And you could have an infinitive number of people in outer space just floating around, right? They don't have the same physics results as you have on Earth.